Alright, so this is day 2 of 10.2, and we're talking about the section on vectors, and we're talking about vector valued functions. Any vector, vector v in this case, from with components a and b, can be written as a linear combination of two standard unit vectors. Now, the I vector denotes movement in the x direction, or left and right. The j denotes vertical movement up and down, or those components of the vectors. So when we see this written in this form with i's and j's, the a is the x part, the b is the y part, so we're going to have ai plus bj. Now that comes from the fact that we can break this thing down right here into the vector a comma 0 plus 0 comma b, x component, y component. And then that can be used. The a can be taken as a scalar component and be taken out. So we've got the point, or the vector 1, 0, which is equal to I, and 0, 1, which is equal to j. That's how you can go through the steps. You don't have to go through those steps. Just understand that if you have a vector v that is in the component form here, a and b, you can put it in the linear combination form of ai plus bj, just going and putting those in front of the I and the j. Now, the vector v is a linear combination of the vectors I and j, where I is the vector in x component form, or x component only, and j denotes the vector in the y part. Now, the scalar a is the horizontal component of v, and the scalar b is the vertical component of v. Now, we can describe the position of a moving particle by a vector r of t, just a way that we could write it. And if we separate r of t into horizontal and vertical components, we can express r of t as a linear combination of standard unit vectors I and j. So we can call this one f of t I and g of t j. So what we're going to end up doing is defining this thing with an x function and a y function. Does that sound like anything we've already done? Hey, what about the parametrics? It's even got the t in there. So this is very similar to using the parametric formula, except we've got a way that's one equation that we express it. Alright, now in 3 dimensions, the component form would become r of t is equal to f of t I plus g of t j and h of t k, where k takes the component, or takes the part of our z component. We still have x, we still have y, we just add the z. Now, I'm going to go through this really quick, but you can graph on the TI-89 using the parametric mode. It also works on the 84. So let's do r of t is t cosine t I plus t sine t j. And t is greater than or equal to 0. You want to do parametric mode. This will be your x equation. This will be your y equation. And there they are. You're going to set your window. This one wants you to go to 8 pi for some reason. So just you can type in 8 pi and it'll automatically put the decimal in there. And then when you do this, and like I said, this is also available on the 84. And with the 84, the way you get the T up is not the T down in the keyboard. It's the T that's there with the X, theta, T, and N. It's that one button that's got all the variables on it. That's the one you want to use for your T there. All right, and then when you put all this stuff in, you're going to get a spiral that's going to look like this. It's actually called Archimedes spiral. All right, now most of the rules for the calculus of vectors are the same we have used, except speed, in this case, is the magnitude of velocity, not the absolute value. It's the distance. Direction is the velocity vector divided by the speed. So you'd have to find the absolute value, well, not the absolute value, but the speed or the magnitude of the velocity vector. You divide that into the velocity vector, and that's going to give you the direction. Guys, the direction will always be something that has a length of 1. It'll be a unit vector. When you're denoting direction only, you'll have a vector that has a length of 1. In other words, it's a unit vector. The velocity vector can be as long as the velocity is. You know, it's got both parts. But if we're talking about just the direction, the dividing by the speed is going to make that thing have a magnitude of 1. All right, so let's look at an example. We've got r of t equals 3 cosine ti plus 3 sine tj. Find the velocity and the acceleration vectors. Well, if this was a normal xy equation, what would you do to the position function to find velocity? Well, you would take the derivative. Well, guess what? You can do the exact same thing. Velocity is nothing more than the derivative of the position function r with respect to t. So we take the derivative of 3 cosine t, and we're going to get negative 3 sine ti plus 3 cosine tj. The 3 cosine t comes from the derivative of 3 sine t. All right, if we want to find the acceleration vector, we're going to just take the derivative of the velocity. So if we take the derivative of this, we're going to get negative 3 cosine t times I. Take the derivative of 3 cosine t, we're going to get negative 3 sine t, j. So the exact same thing we've currently or have previously learned about velocity, acceleration, and position, their relationships are still going to be the same. It still holds true. And it makes sense because what is a derivative? A derivative, the derivative of the position with respect to time, how position changes with respect to time, is called the velocity. That's what we're looking at. Now, find the velocity, acceleration, speed, and direction of motion at t equals pi over 4. So all we're going to do there is we're going to take these values for velocity and acceleration, and we're going to put those, we're going to put t equals pi over 4 in for everything up here to calculate it. And when we do that, the velocity is going to be 3 sine of pi over 4. Well, sine of pi over 4 is the square root of 2 over 2. And cosine of pi over 4 is the square root of 2 over 2. So you're going to have negative 3 square root of 2 I plus 3 square root of 2j. Now notice this is not something that's not just a number. The velocity we're looking at what is the velocity at this moment in time, and it's got an x component and a y component. They just both happen to be same values except one's negative. All right, we do the same thing when we do the acceleration at pi over 4. So we have a of pi over 4 We plug it into that acceleration formula that we found just a second ago. So we get negative 3 cosine pi over 4 times I minus 3 sine pi over 4 times I. And sine and cosine of pi over 4 is still square root of 2 over 2. Or 1 over the square root of 2. And we end up with these. That's what they're using here. That's why they get the negative 3 over the square root of 2. They're using for the cosine pi over 2, 1 over the square root of 2. Now if you work that out and rationalize it, you end up with 2 over the square root of 2. So these are equal. But that's what they're using for cosine and sine of pi over 4 is 1 over the square root of 2, and it makes things just a little easier. I mean, it's not a big deal for you to rationalize the denominator. All right, and so there's our velocity and acceleration we've just calculated. So let's find the speed and the direction. Well, the speed you want to find first. And that's just going to be the magnitude of the velocity at pi over 4. So you're taking the magnitude of this thing right here. And remember, that's nothing more than this thing right here squared plus this thing right here squared, added together, and then take the square root of it. So we're going to end up with negative 9, or net 9 halves plus 9 halves, which gives you 18 halves, which is 9, and the square root of 9 is 3. So the speed at pi over 4 is 3. Now what about the direction? Well, the direction, if you remember the direction of motion, we're looking for the velocity vector, and we're going to divide by what the speed is. So the direction is going to be the velocity at pi over 4 divided by the magnitude of the velocity at pi over 4. So that means we're taking this thing right here and we're dividing it by 3. And we can do that into both parts, because remember we're dividing by a single term. So we can divide that into the first one, divide that into the second one. Of course the 3's are going to cancel out. So we're going to end up with negative 1 over the square root of 2i plus 1 over the square root of 2j. So this is the direction. And if you took this, squared it, and this, and squared it, and then added them together and took the square root, you're going to get 1. That's because this is a unit vector. It has a length of 1. That's what a direction is. It's not having the magnitude in it, it's just telling what direction you're going in. Because we've actually taken the magnitude out of it right here by dividing by it. Alright, so here is another vector equation, and we're going to write the equation of the tangent where t is equal to negative 1. Now the tangent of r, remember we're going to have the slope, we're going to have the point. So at t equals negative 1, r of negative 1, you plug that in and you plug in chug here, you're going to get negative 5i plus 11j. That's the x and the y part. And the velocity at negative 1, otherwise known as the slope of this thing, is 12i minus 9j. So its position is negative 511, and its slope is going to be the magnitude of this. Actually, no, it's not. It's going to be the x over the y, because it's rise over run, y over x. So it's going to be negative 9, that's the y part, rise over 12 run, that's the x part, so we end up with negative 3/4. So that's something that is new. Remember, we've got two components here, so we've got to remember what the slope is. It's rise over run. In this case, it's negative 3/4. So when we put all that together, what's going to happen? Well, we're going to have y minus 11 equals negative 3/4 x minus a negative 5, or plus 5. All right, and there's your point slope, and you can leave it just like that. They went ahead and put it in slope-intercept form, but it is not necessary for your work. Actually, I don't want you to do it. All right, so now the next part for the same problem, find the coordinate of each point on the path where the horizontal component of the velocity is 0. Now, what's going to tell me about the horizontal component of the velocity? Well, if we find the velocity, the horizontal component is going to be the x, or the I part. So 6t squared minus 6t. If we want to know where that's equal to 0, what values of t that makes that 0, we just pull that thing out and set it equal to 0. And then we can factor out a 6t, divide out the 6, and then factor out a t. Either way, you're going to have a t value of 0 and 1. So that is the t values for where we're going to have a horizontal component of the velocity that's equal to 0. Now, that's the t value. They actually want the coordinates of the points, though. So now I have to take the 0 and put it in here and here to find the x and the y part. And then we have to plug in the 1 here and here and put in the components for the other part, the other point. So when we plug in 0, we're going to get 0, 0. And when we plug in 1, we're going to have 2 times 1 minus 3 times 1. That's going to be negative 1. I and 1 minus 12 is going to give you negative 11. So we're going to end up with negative 1, negative 11. So as you can see, these are not real difficult to deal with. You just have to make sure that you're keeping it. It's just another way of expressing a point, another way of expressing the x and y part that you have to get used to and make sure that you understand and you're interpreting it correctly.